In this video, we're going to look at how light behaves like particles now. And to begin that story, we have to learn about the photoelectric effect. And the photoelectric effect is simply that when you shine a light on metals, some of these metals will emit electrons. And the photoelectric effect is what actually gave Einstein his Nobel Prize. He was able to discuss it and show that light behaves like particles. Now, before we knew light was like particles, and if you just think of light like waves, you would think that the light energy that is being shown at the metal goes right to the electrons. Therefore, if you have shorter wavelengths, that is light with more energy or a brighter light, you would expect more electrons to be ejected because you need energy to eject these electrons. So as we saw in the previous video, if I have a light that's brighter or a higher wavelength, it has more energy in it because the energy of wave directly proportional to its amplitude and its frequency. So if you have a dim light that is low amplitude, then you would expect it would take some time before electrons are emitted because low energy is being shot at the metal and you need a lot of low energy to eject an electron. All right. And so let's take a look at this actual experiment. So in this experiment, we have two lights that are being shown at two different pieces of metal. Here are the frequency of light and the rate of electron ejection. Blue is a high intensity light, more energy. Red is a dimmer light. So both lights, as you change frequency, as if you're in low frequencies, you get no electrons ejected. But once you hit a certain frequency, both the low intensity light and high intensity light will start ejecting electrons. And it's true, if you have a higher intensity light, you will eject electrons faster than your lower intensity light, but there's no lag phase. No matter how much light you show in the low frequency, be it high intensity or low intensity, you will never eject an electron. Therefore, if you just think of light as waves, you're missing something. Because with waves, you'd figure the energy keeps crashing into the metal over and over and over in a continuous way. Get this continuous energy. And that's why they thought of this lag phase. But you don't see that. You see none, then ejection. So light or energy isn't continuous crashing in. It's being sent in packets, discrete packets. Right? And so Einstein said, okay, light's coming in discrete packets, so it can't be a wave. They have to be particles. And he called these packs, particles, quanta, or photons. And he said that the energy of a photon is directly proportional to its frequency. That is, the higher frequency, the more energy you're showing. And we saw that in the previous slide. To eject electrons, you need a certain frequency of light. Now, the energy is also inversely proportional to the wavelength. Shorter wavelength, higher energy. So X-rays have very short wavelengths. They're very high energy. And the way to calculate this is E equals hv if you have a frequency, where h is what's called Planck's constant. And it's just a set value. You don't have to memorize this value. This will be given to you. But know when you want to go between energy and frequency, Planck's constant is how you convert between the two. If you want to convert between energy and wavelength, you need Planck's constant and the speed of light. So energy equals Planck's constant times the speed of light divided by wavelength. So just so we are all on the same page and know how to use this, if I have 1 mole of photons that is in the infrared radiation spectrum, that is 1500 nanometers, how much energy do I have? So go back to the previous slide where your equations are and see if you can answer this. Alright, so our equation equals E equals hc divided by lambda. So my energy equals Planck's constant times the speed of light. Make sure your units all work out. Divide it by wavelength. Note that I converted these to meters so my units would work out. I solve that. I get my energy is 79.7 kilojoules. Alright. Well, let's go back to the photoelectric effect. Now, the amount of energy you need to put in to eject an electron is called the binding energy. Now, shorter wavelengths have more energy, so they give more energy to electrons. So the light's coming in, short wavelength, a lot of energy, hits the metal, transfers that energy to the electrons in the metal. Any excess electrons is kinetic energy, that energy of movement. That's what ejects the electrons from the metal. And we have kinetic energy equals the energy of the photon being shot minus this binding energy. And we just talked about what the energy of the photon is, and here's our symbol for binding energy. So let's just make sure we have this topic down. So if I have metal that will eject electrons when struck by yellow light, what will happen if I strike it with ultraviolet light? So there are your 4 options below. Pause the video, see if you can pick it out, and come back when you have an answer. Alright, so the answer is C. It's ultraviolet light, more energy, so you will definitely eject the electrons. And since you have more energy than the binding energy, all that energy is going to be converted to kinetic energy. So they'll have more kinetic energy than the yellow light. Alright, that's all for this video. See you in the next video.